A small box set to launch to the International Space Station will soon recreate the coldest spot in the universe. The box is equipped with lasers, a vacuum chamber, and an electromagnetic knife that can cancel out the energy of gas particles to freeze atoms to a point more than 100 million times colder than the depths of space. Once these atoms have been cooled inside the box, known as the cold atom laboratory, they can form a distinct superfluid state of matter called a Bose-Einstein Condensate. The cold atom laboratory was created by NASA's Jet Propulsion Lab. It's now in the final stages of assembly, with plans to launch this August on SpaceX CRS-12 to the International Space Station. The instruments can freeze gas atoms to just a billionth of a degree above absolute zero. According to the researchers, studying these hyper-cold atoms could reshape our understanding of matter and the fundamental nature of gravity, said Cal Project scientist Robert Thompson of JPL. The experiments we'll do with the cold atom lab will give us insight into gravity and dark energy, some of the most pervasive forces in the universe. At these extreme temperatures, the atoms will form a state known as a Bose-Einstein Condensate. In this state, the condensates are a superfluid with zero viscosity. This allows the atoms to move without friction as if they were all one solid substance. Then, they can be observed more like waves than particles, as rows move with each other like mysterious waveforms. But they've never been seen at such low temperatures as Cal will achieve, according to NASA. The space agency has never created or observed this state in space, and on Earth, the pull of gravity means they are only observable for fractions of a second. In the microgravity on the International Space Station, though, these atoms will be able to retain their waveforms for much longer, giving scientists a longer window into their behavior. The researchers predict the setting will allow the condensates to be observable for up to 5 to 10 seconds, and one day, this could be brought up to hundreds of seconds. If you had superfluid water and spun it around in a glass, it would spin forever, said Anita Sengupta of JPL, Cold Atom Lab project manager. There's no viscosity to slow it down and dissipate the kinetic energy. If we can better understand the physics of superfluids, we can possibly learn to use those for more efficient transfers of energy. 5 teams plan to run experiments with the lab, including Eric Cornell of the University of Colorado Boulder in the National Institute for Standards and Technology, one of the Nobel Prize winners who first created Bose-Einstein condensates in the lab in 1995. The experiment could pave the way for improved sensors, quantum computers, and atomic clocks for space navigation, and it could shed new light on dark energy. This means that even with all of our current technologies, we are still blind to 95% of the universe, said Kamal Udriri of JPL, the Cal deputy project manager. Like a new lens in Galileo's first telescope, the ultra-sensitive cold atoms in the cold atom lab have the potential to unlock many mysteries beyond the frontiers of known physics. The cold atom lab is now moving through tests to prepare it for delivery to Cape Canaveral, according to Dave Avellini, the test bed lead at JPL. The tests we do over the next months on the ground are critical to ensure we can operate and tune it remotely while it's in space, and ultimately learn from this rich atomic physics system for years to come.